But and then we can probably start. We have a pretty good quorum now.
Yep. So I think this is a good place to get started. We all know Tilman now, so why don't you just go ahead and get started, Tilman? Thanks.
Okay, great, thanks, and welcome you all again for the lecture. It's great to be with you as much as possible. Yeah. Okay. So we had yesterday looked at this system. This standing wave reflected from a mirror, and then we realized, oh, what a pain, because it has all this time dependency in it, and then we kind of came to the conclusion that we need a different approach to approach these problems. And one way is to find, and that's more or less where we ended, that we find steady-state solutions to the time-dependent Hamiltonian, and then that we expand in these Floquet states our eigenstates, our states of our problem. So maybe let me have a look. What were the main points? Okay, so one point is shown here. That's a way how you can look at the time evolution of a state. You have your evolution operator here, and you can separate it in two parts. In one part where you look at full periodic times, and that kind of governs the long-term dynamics. And then you have the short time evolution, and that we have phrased in terms of kick operators. And this, okay, that is one way how one can write it, and that's written in the term that it's the effective, that we have an effective Hamiltonian as a Floquet Hamiltonian, which is gauge independent. Or the gauge independent in the sense that we always need to keep in mind that in the periodic problem, we have to start at some point T0, we often call that. And that we need to decide about that. And in this way to write it, this is all absorbed in this kick operator. That's one way, but the alternative is that you have here also dependency on this, what we called T0. And then we noted that this Floquet Hamiltonian, that these quasi-energies, because we can only look at it in terms of quasi-energies because they're only defined in modulo h bar omega. Okay, and here we basically, that's how we evolve a state. You write it in terms of these Floquet states. They are written down here again. So this is the same as this one. And the nice thing is you have here time-independent coefficients, and here your quasi-energy. So it simplifies the problem quite a bit, or you can treat it better. And of course, you want to get expressions. What is your effective Hamiltonian for your problem? You can also, of course, look at the observables, and you can get, for example, I mean, this way here is described how you can get time observables, expectations values for your Floquet eigenstate. So that is this oscillating, and these observables, then they oscillate. I mean, if you don't average, they oscillate at the driving frequency or higher harmonics. So, well, with atomic physics background, for me, it's always, I mean, like the dipole moment, which in reality is oscillating very fast. And of course, the Rabi oscillations, they are much on a much slower time scale. And also, with the, if one wants to have analogies for this time phase, for this gauge of the phase, is what we call T0. One can also look at it in terms of this short pulse physics, where if they have very, very short pulses, then of course it will play a role where you have your zero, or how your envelope is positioned, pulse envelope is positioned with respect to the fast oscillation. So it's not that it only pops up here, it pops up in different parts of physics, and often in different phrasing as usual in physics, and then one needs some time to realize that the others are doing the same or whatever, or the others realize that we are doing the same. Okay, and one can look at it in also in here in the diagram. Well, there I looked. Well, here is shown a drive, and then say you have some state, and then you write this state in terms of the Floquet states, superposition of the Floquet states, and then you will see that you have the kind of a slow evolution of the observable, and a fast one that's a non-time averaged, which is oscillating around this value, and the slow one that is governed by the Floquet Hamiltonian. So that's okay. So that's where we are now, and one can now ask the question, and before we went then, as we did yesterday, but a bit more PowerPoint today, so we will have time also to look at how we do the experiments. There is the question, how get I insight into the system, or how get I hold of my Floquet Hamiltonian? And of course, that can only in almost no case be calculated in closed form. So what you want to have is some form to approximate, and that is done with what's called high frequency expansion. So what you do is you take your system, and then you look at a separation of energy scales. So you look at the question, your omega, is it large compared to other energy scales? And then you can expand in powers of omega. And then you get an effective Hamiltonian, which, well, you can write as the whole series of 1 over omega, 1 over omega square, and so on, and it's getting smaller and smaller, the contributions. And in the typical situations where one is looking at is that you have the first, the n equal 1 term, but also often the n equal 2 term in your problems. And so if you, in general, well, I will not go too much into detail into these terms. But the zero order that one finds, so you expand here in the different orders. That's this term here, and this the zero term expansion is what you do is you average over the whole period, the Hamiltonian. And here, the zero order, that is the static part. So that's the non-driven system. And then you get in this form here, you get your first order, and then you get correspondingly higher orders. Of course, you can continue that depending on how good your stamina is for writing down these expansions. And of course, some people are better and some people are not so good at doing it without a mistake. Of course, it doesn't help the stamina. It doesn't converge. Okay. And a way to calculate the eigenstates then of your Hamiltonian, that is the extended Hilbert space. And a way to look at this extended Hilbert space is that we had discussed at the very beginning that we can look at the system that if we have a modulated standing wave, we can absorb energies from the light field, or we can have atom light states with say n phonons, if we call the Raman difference a phonon, or n+1 phonons, n+2, and so forth. These are all equivalents. So in that sense, we get a whole energy spectrum. And this energy spectrum, well, you can write it down in this form. And if you now look at what this Hamiltonian looks like, this extended Hilbert space, which is overcomplete, then for a simple example, it has this tri-diagonal matrix. And that is the first order. If you expand into second order, you get additional terms here. And now there is then the question whether you are in a weak or strong driving regime.
So Tilman, can I just make a comment? Because I remember when I was first learning this, there was one, this looks very much like an ordinary Hamiltonian matrix, except the energies go infinitely negative, right? So, yes. So this causes some pretty big differences from normal Hamiltonians when you start to think about it.
Exactly, and the way the way I look at it, but I'm happy to discuss it, is in a way like with dress states. In the end, if I take dress state pictures with photons, and I'm in the limit of a large photon number, not the nice one in the James Cummings where I start at 0, I know where my vacuum is, but when I'm way up in the ladder, and then I can go down or I can go up, it is all the same. In a way, it's a slight approximation because we ignore the ground state. So you would also look at it in that way, or a way to look at it.
Well, this infinite negative energy or infinite positive energy, I think we can think of it as because it's really periodic in the energy. There is no energy here. It's a quasi-energy, right?
Mm-hmm. In a way, well, my intuition, my argument would be, we don't know for how long the system has been running in a way.
Right. Mm-hmm.
And then we could have put in energy or taken away energy.
Mm-hmm.
That's...
Yeah, good point, yeah.
But any other further thoughts are also welcome from... Maybe there are, at this point, some... Okay, then... and okay, and then the system of very weak driving system, then you get out of what was written down here. If you are in the weak driving regime, then you get back the familiar rotating wave approximation, and kind of where there one feels again on more familiar ground. Okay, and here it says now PowerPoint. So we will move now again to the experiment. And in the experiments, we will, in this round of PowerPoint, we will use lattice shaking, and it will probably, I hope, motivate that we then look again a bit more precisely into lattice shaking. But let's first have a look what one can do. And I think there was a topology lecture just before, I think. Yeah. So
I think there's a question. Was it Storm?
Yeah. Could you explain how the weak driving regime, as V shrinks, it seems like these off-diagonal elements, those are the ones getting smaller. Why does that allow us to single out a block from this matrix? It looks like
because they get smaller and smaller, and you can ignore the coupling. There is it's sufficient to then. I mean, you take the time average. I mean, like in the rotating wave approximation, it averages to almost zero. But if you have, say, if you drive strongly, then you have to take into account higher order.
I guess my question is that each block that you could dissect out of here would be equivalent. So how do you choose which block to cut out as the important block?
I start with one.
Okay.
And choose. Yeah, I choose one. I start with one energy, but where I don't know. This is in a way a bit a preparation, a question of the preparation of the system. I see it like, well, if you take with a two-level system, if you go into a light field, well, you have to start somewhere, and then maybe at which energy or how many photons you do count as contributing to the energy of your system.
So in this approximation, we would not be able to like drive coherent oscillations between the two states because the driving is too weak.
And no, this would be just the coherent driving, but not more.
I guess my point is
not the Bloch-Seeger shift, for example. Then you would have to take into account more additional couplings, which is in a way you take into account multi-photon processes.
Okay.
Bloch-Seeger shift is, if you will, for the experimentalist, it is that you have a dipole trap. Usually, well, you go off resonant, and you have, say, you have your rubidium, and then at some point you might go very far off resonant and very strong in your laser, and then your rotating and counter-rotating terms, they are no longer. You have to take into account the counter-rotating terms as well.
So I think one thing to keep in mind here is that, you know, eigenstates aren't magic. It's just the eigenstates give you a recipe for computing dynamics and things like that. And that's true whether you're doing Floquet or anything else, right? You have to say, what is my initial condition? And then using the eigenstates, this gives you a prescription to evolve the time evolution, right? But it's not like the eigenstates tell you the physics on their own. You need that initial condition.
Yeah, I think my question wasn't very clear. If we were to start in, let's say, like one step of the ladder, like in the middle at H0 where there's no H bar omegas, because these V's are symmetric about there, how do we know whether to take the upward or downward step in our block? It's symmetric. That's really the question.
I mean, it doesn't matter, of course, which ones you take. And because you could just take one photon away again and have the same result. So that's the level I can answer. Okay. 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 We wanted to come to PowerPoint. Let's see. I have two options. Either I move. I'll try that now. I move to the other computer and see how that works. You can't share screen. I have to stop sharing and then take the other one probably to share.
I can if you've got it hooked up.
I think it's okay. I will probably manage it. I think it should work. I hope. Share. You pop up here to the side. I just need to change my camera, otherwise it looks funny. So now I look at you here, and now I switch on the presentation. And you are all here. Well, I'll put you here. Okay, so I see you now here. Okay, good, wonderful. Okay, so that's basically, I mean, you remember that we put together our optical lattices. We overlaid different interfering lattices, and then we could get this system. Let me here see, this system where you can generate different interference pattern. In particular, and that we will briefly look at, is this hexagonal graphene type of structure, because that will lead us, when we shake it, it will lead us to a topological Hamiltonian. However, we start with this graphene. So you remember it has this band structure with these two Dirac points. And of course, as an experimentalist, the question is, well, it's nice to produce that structure, and then you can say, you have produced this structure, but then people also want to see, do you have indications that you have Dirac points? And there is a challenge with the Dirac points. At the Dirac points, you have vanishing density of states, and you want to measure a kind of a very small energy scales, because I mean the Dirac point, basically there is a zero gap. And to translate that, vanishing density of state, one would say, okay, there is no signal, almost no signal, because it's vanishing density of state, and small energy scales, that would mean you need infinitely long time to measure. So it is not so obvious how one could do that. So I want some suggestions how one could. I mean, imagine you're in the lab, you know more or less, yes, we do have this graphene type of lattice, but how can we convince other people that is actually that we have Dirac points, which is kind of the hallmark at this point. And I need to see where are the chat. Okay, so you might just raise your voice or you chat.
Yeah, and I'm keeping an eye on the chat if anybody has a question.
Sorry?
I'm also keeping an eye on the chat, and I'll
okay,
let you know if anyone
good.
has a
Yeah,
question.
I have it now also on my screen now, so I think I
think
so just yeah, please.
one possibility is to do an interferometry around the Dirac point.
And in the ferrometer around the Dirac point, that is cool. How would you arrange that? Yeah.
I guess so. This is based on sort of Charles' idea from the other lecture, but basically the Dirac point, we know that there's kind of a pi phase. So if one is able to prepare basically a superposition of plus and minus state, and then just move the atom cloud with a spin-dependent force one around each side of the Dirac point, when then can collect on the other side and do an interferometry.
So kind of in the ferrometer, like, I mean, people did interferometers in free space, and now you suggest to do it in quasi-momentum.
Exactly.
Yes, that's absolutely a good idea, and actually also that's been a work on that, very beautiful work in the Munich group. Other suggestions, or just mentioning what the problems are? I mean, that often is also whether there are further problems or ideas which may not work.
Another possibility is to try to see the dispersion, because if it's linear and we prepare a wave packet, everything moves at the same velocity. So the wave packet shouldn't disperse too much. And we should be able to measure the linear velocity.
And here another way of thinking about is the similarity to one-year Stark localization, with V being tunneling elements and H bar being the lattice till for small tunneling.
Yeah, that was a much earlier comment, I think, on the discussion about how to choose matrix elements. But there was a new suggestion from Abel. Do you want to unmute?
Sure. So my idea would be maybe to exploit the fact that there's a large band curvature at the location of the Dirac points, but I'm not sure if it would actually work because of the vanishing density of states.
Very good. Yes. Yeah. And I think let's just see what we did back then, and then we can discuss further. So the vanishing density of state, in a way, the way we avoided that, or that problem, is that we accelerated a wave packet, in this case a wave packet of fermions, so that you have kind of many fermions going through the Dirac point. So in that sense, by doing a dynamic experiment, you avoid the vanishing density of states. Let me here I need somehow the forward. Okay. Okay. So what we did is doing Bloch oscillations inside the band structure of this graphene type of lattice. Okay, so and that we did with a magnetic field gradient, and so here it is shown, well, what happens if you don't pass through a Dirac point. You just get Bloch oscillations, and if you pass through the Dirac point, then comes what one of you mentioned. Then you may cross this not avoided crossing, this real crossing, and go into the higher band. And then you can measure by band mapping. We had a look at it last time at the very beginning, that you can do band mapping in these systems. And then you can, so this is now kind of images taken after different times of Bloch oscillation. So you see the Bloch oscillation, but what you also see that here in the higher band, population accumulates and it is taken away from these lower bands. So this, in a way, is nice and, well, yes, people may believe. However, then people might not say, yeah, but why? How do you know that it's really a linear crossing? I mean, is there anything indicating that? And that kind of came to us as a, well, because we measured enough, and then we took the data, looked at the data, and then the interpretation of the data gave that result. And that is shown here. So what we did is we did take phase diagrams with and without Dirac points. So these are just intensities of the optical lattices so that we can get the different structures. And below this dashed line, kind of here in this region.
Sorry, Tilman, just is the vertical axis Vy?
The vertical axis is Vx.
Oh, it's Vx and Vx bar.
X and Vx bar, yes. And this Vx bar is this additional laser beam with which we are able to create the Dirac point that basically shifts the other band structure in energy and has points where they have the same energy eigenstates so that you get a crossing. So these are the two coordinates, and the third, I mean, the colors here, that is a transfer to the higher band. So when it's red, you have more transfer to the higher band. And the difference between left and right is the direction in which we applied the magnetic field gradient. And so then one sees a difference here between those two phase diagrams. I mean, the line, I mean, this dashed line where you start to have Dirac points, that is roughly at the same point, the same reach. I mean, for experiment, we are quite happy. But it looks different. I mean, the how it builds up and so on, and here is something missing. Seems so. What? Maybe maybe I can put that as a bit of a question. How well? What is the possible interpretation of that these phase diagrams? So we had to think hard. It was worthwhile because we measured, I think it was 80 hours in one go. So it was really a tough measurement now. So are there suggestions, ideas, thoughts, what could be, why does it look so different on the left and the right?
Could you explain again what the axes are? I didn't catch
Yes,
that.
sure, absolutely. The axis here, maybe I go back a few slides, then let's go back. Okay, so the axis is the intensity Vx bar and Vx. And that's the intensity of this beam versus that beam, and that has that is here again here an increase in Vx bar. So here you have a certain Vx bar, and here it's lower. Well, and here is just as comparison as a 0 for that one, but this is not on this line. So what will happen if you change this Vx bar is that you go kind of through the different structures you have by reducing. So you will have this honeycomb, and then it will get dimerized. And you will have at a certain value, your Dirac points will disappear. So you will have they just touch, and then they don't touch anymore.
So let me see if I understand the question you were raising. So you're asking, why does the left plot and the right plot, why don't they look the same? Is that essentially the question?
Yes.
Maybe to stimulate discussion on this, I would ask, why would I expect them to look the same?
Yes, so anyone can answer.
I just have another question. What is the color? What does that represent here?
The color represents how many atoms are transferred to the higher band. Kind of how many atoms have gone through the Dirac point in the higher band. In that sense, the blue region here makes a lot of sense because there is a gap. And no atoms will be transferred into the higher band because there are no Dirac points. Only once we have Dirac points, we can transfer into the higher band.
So it seems like in the left plot, there's a region where if you continue to increase Vx bar, you go back to having no transfer to the upper bands. Whereas in the right plot, that doesn't seem to be the case unless we just have cut off at some point. I have no idea why. I'm just
no, but you have wonderfully, carefully phrased it because you said that no atoms go through a Dirac point or something, and not that there is no Dirac point. And your phrasing was exactly the correct one. What is happening there is that since we have only a cloud of atoms. In this, let me go back one, in its trajectory, when you pass through this trajectory here, you may, because depending on where you are in this diagram, these Dirac points move in space. And then your cloud might miss the Dirac point, simply spatially or in terms of quasi-momentum. So they might not go through a region, they might not pass. So you can imagine if the atoms were, let's say, if I go here an atom and then it's if an atom starts here, it's reflected and it goes there, then actually it will not go through a Dirac point. So there is simply in a way a trivial reason because your wave packet missed the Dirac point. That's exactly that one. But there is the other feature that here you very rapidly have a sharp increase in the number of transferred atoms, whilst here it's super smooth. So what would you look at? Maybe what, I mean, if one is searching for a solution, what would one maybe look at?
Maybe the one on the right, I'm just guessing here, right? Maybe you slightly open the Dirac point, so you have a slight band gap, but it's very small, so you get kind of Landau-Zeno transitions to the higher band, but it's kind of smeared out because there's no spectral width.
Yes. So but let's have a look at the band structure. Okay, so what they feel, and that's now that is the band structure. Or symbolically, when the Dirac points just appear, when they kind of are born, the Dirac points. It's like, I mean, for those who are doing atom trapping, or maybe one or the other person remembers the quick trap, there you have two quadrupole, out of two quadrupole traps, when you merge two quadrupoles by a field offset and to get a kind of Joffe type trap, then you go through a region where you are harmonic in one direction, there it's of course in space, and linear in the other direction. And that's, I mean, that's has some topological reason. You have heard it in the last lecture. So when you have these two quadrupoles merging, then you have this feature, and the same feature seems to be exactly in quasi-momentum space. And then now, if you have this quadratic touching, there your eigenstates here, that stays the same. Here, the eigenstate really with maybe the little opening or no opening, the natural eigenstate goes up there. But here they're orthogonal, so there is no, it would adiabatically, kind of the adiabatic following will be staying here and not the crossing into the higher state. So there is no Landau-Sehner. So here it's not linear. Here it's a quadratic touching, and here it's a linear crossing. And this quadratic touching means that you very slowly build up population. So only once you actually start to, well, if you go further, then you start to have Dirac points. So then you also in that direction, then you get linear crossings. But at the beginning, it's just a quadratic touching. And that was for us, I mean, kind of we looked at these phase diagrams, and then, and also there came out a paper, well, around that time, or there was a preprint already, I can't remember, from Montabaur group, and they did simulations, and there one could also see it now. So that showed that actually one has this linear, or I find it from an experimental point of view quite a nice way how to show it. Okay, but let's move on.
So also, I can imagine that these results depend on how fast you sweep, the rate that you go through the Landau-Sehner transition. I guess if you go slow enough, maybe it just scales things. But can you just elaborate a little bit more on what's happening there?
Yes, that is the question of how strong a gradient we put, and that would give us a speed with which to go through. Yes, absolutely. Yes, that's yeah. It's it also, yeah. This determines always the energy scales, or the gaps determine the energy scales. If you want to stay in the lower band, then you need to make sure that this gap is large enough.
So I guess that speed, or that gradient sets the size of what is the minimum gap you could resolve, right? So I guess one question I would have is, how does the minimum gap you could resolve compare to your bandwidth here? Is it 1/10 or 100th, or how sensitive are you?
Yes, so these numbers. I think it is always on the order. I think we can resolve 100 Hertz, 200 Hertz gaps. That's what we are. If we are a bit below that, then we can typically we think, okay, that will work. Yeah, that's the number I have in my head now. Yeah.
Thanks.
You're very welcome. Okay. Okay. So what? Yeah. So what's happening here? To break the inversion symmetry, what does one have to do? That's now a question. I mean, you have the Dirac point, and then obviously you want to also destroy it. And you want, for example, to destroy it in a sense by breaking the inversion symmetry. So how can one do that experimentally? Anyone?
An additional lattice?
Yes, definitely. One could definitely. Oops, no, that's not where it was. Yes, but even easier in the setup that we have discussed. I'll go back to the setup. A few clicks away. Ah. No, nothing to do with that, nothing to do with that. Something to do with this. Which parameter will break it? Or on which parameter do I have to tune, or on which parameter does it depend, this symmetry? Theta, yes, exactly, yes. It is this one. And that one determines the position of this standing wave on the maxima with respect to this one. And if we have, if you want to have Dirac points, then it must be shifted. The maxima must be shifted exactly on the minima. So it needs to be very precise. And the nice thing in this setup is that is kind of, it depends. Of course, I mean, what is in reality is this has a slightly different frequency. So this means also slightly different wavelengths. And so you can choose a wavelengths such that this is exactly shifted. And you can now tune the frequency to fine tune. So it's encoded in a frequency which you always can control very well in an experiment. So if you then tune to another frequency, then you break the inversion symmetry. Okay. And there was also, and that is the paper with the interference around the Dirac point. That's I think this. Yeah, I think that's that paper. Okay, Duca et al. It should it be? Well, okay. And now one can. Yeah, sure.
That is the paper I checked.
Okay, good. So it must be et al. Yeah. It's, I think, Uli Schneider and Emanuel Bloch. And other people also work with that.
Yeah.
And well, now let's look at there is also a consequence of this. Well, when you go around, you accumulate the phase shift, but also you have a consequence, and that probably, I assume that also Nigel mentioned, that you have for the semi-classical motion, you also have a consequence of this Dirac point. So if you think of your particles moving through, you accelerate a wave packet and it moves through your band structure and sees or passes by, close by an open gap, then there is a Berry curvature, and this will lead to deflection of your particle, and the equations are written there. And you can think of it as, I have to go to the next slide, yes, that in particular, the closer you are to the Dirac point, then you get kind of a drift in the motion. So it does kind of a jump to the side. And then you could wonder, okay, can't I? It would be nice to measure that. And from experimental point of view, well, you can then say, okay, so it jumps a bit to the side, but on the other Dirac point, it jumps back. So there's not much to measure because, well, you would have to measure half a Bloch oscillation or something. And then you could also think, it would be much more fun if, well, if you had Dirac points where the Berry curvature, well, I did not mention, it jumps back because the Berry curvature has just a different, well, it is in the one case positive, in the other case negative, so that it goes to the right or to the left. So it would be nice to have a band structure where it always goes to the right, and, well, very pragmatically, the signal bit would be larger. And also that would, of course, be like a Hall current. So you send your current and you would get deflection in perpendicular direction. But then one might wonder how can I construct such a situation where I have Dirac points which have the same Berry curvature. So that's also a question to you now. I know who has answered the question originally, but let's see. I mean, what could one do? I must admit, I wouldn't have had a clue. But it doesn't mean that you don't have an idea how one could make a band structure which has two Dirac points with the same Berry curvature.
You're going to want to break time reversal symmetry, right?
Yes.
And like, I mean,
yeah.
Are we still working on the honeycomb?
Yes.
Model?
Yes.
So we can just do like the next nearest neighbor hopping that we learned about in the Haldane model.
Mm-hmm. Mm-hmm. Exactly. Yeah. Mm-hmm. So
I think.
Yeah. You go.
Oh no, I was just going to say, I think if you tune the energies at like basically like along the the coefficient of like sigma z at
Yes.
the two Dirac points, or like what would be Dirac points if there was no gap.
Yeah.
If you make those have opposite signs at the two Dirac points, I think you can get the same. I think maybe you can get the same pi phase.
Very good. So let's see what I have on my slides. Okay, so I have the reference to the proposal by Haldane, a quantum Hall effect without a magnetic field, and the basic idea being, as you said, breaking time reversal symmetry. And oops, why does it not click? And the idea, the starting point was in his work was exactly Haldane, a honeycomb lattice, and then breaking time reversal symmetry. And of course, the question is how one can break time reversal symmetry. And that's for theorists easy. I mean, well, as a theorist, you just, I mean, you just write down this additional complex tunnel next nearest neighbor tunnel couplings, and then you can get a Hamiltonian which breaks time reversal symmetry, and then you can study it. And then you see that you get that when you include this additional tunnel couplings, and here I would like you to remember that they have a phase phi, and because later the plots will be as a function of this phase phi. And if you include that, then you open up the gaps, but the Berry curvature is the same on those both former Dirac points. And the phase diagram, well, okay, then it's a Chern insulator with non-zero Hall conductance, and the phase diagram looks like this. So you have here on the x-axis, so horizontal axis, there this phase of this tunnel matrix element is plotted, and on the y-axis the inversion symmetry. And so you have a perfect inversion symmetry on kind of this line, and you may have some broken inversion symmetry on this line or on this line. And this center point, that is the perfect graphene lattice. And this red region, that is where you open up a gap and have a negative Berry curvature. And here on the right-hand side, when you open up a gap and you have a positive Berry curvature. And now one might wonder what's happening here on these borders. So what is, I mean, what's happening? I mean, here we have, well, different Berry curvature. So here we have a normal either insulator if we have an inversion symmetry. So what is this line determined by? It looks so nice here. It's a really sharp phase change. What's happening here? If one thinks of, say, the band structure of the system. Or what could happen? I mean, one can simply guess what can happen.
Is it where the bands touch and we have?
Yes.
And we have like the bands closing and then changing their character?
Yes, that's correct, absolutely correct. One can still be a tiny bit more precise. I mean, what I have here a crossing and I have there one, for example. One could be a tiny bit, I mean, I'm totally happy, of course, with let's see whether I can also, okay, so what is happening there is you have, I mean, as you said, the bands are open. There is a band gap, and the Berry curvatures have both the same sign on both sides, on both Dirac points. And then here it kind of closes one Dirac point and then opens up, but now with the different Berry curvature. So that's determines this phase line, and of course the other Dirac point down here. That's okay. And then the question is how can one build such a model? And there we can also get inspiration from Haldane himself. And his inspiration that he gives in his paper is, while the particular model presented here is unlikely to be directly physically realizable, it indicates that at least in principle, the quantum Hall effect can be replaced in the wider context of phenomena associated with broken time reversal invariance, which is, of course, nice that he wrote it, he formulated in that way, that it's so difficult. So it's always nice if they theorists say that. And then came another proposal that came out by Oka and Hideo Aoki. And they suggested, well, a proposal to see what they call the proposal for photovoltaic Hall effect in graphene. So that was more actually, I guess, from an applied side. So one could imagine that if I can switch on and off a Hall effect or even a quantum Hall effect by photons, this is really a nice, crazy idea. And there the idea was that you shine circular polarized light on graphene and thereby induce these, as were mentioned earlier by you, this next nearest neighbor hoppings. So basically, the idea was that you shake your lattice around or shake your structure around, and that you could do, for example, with circular polarized laser light. And he passed by ETH at some point, visiting Manfred Siegrist, and he wanted to talk to us. And we fortunately we thought, oh yes, let's talk to him. And there he suggested maybe optical lattices. I think it's in his proposal also. Well, then we discussed, could it be, well, at least the idea that in principle that might be realizable, he conveyed to us. And then we had a master thesis that was Martin Lebrun's master thesis that Gregor Yotsu then supervised. There we calculated to see, does it fit for our system? Will the band gaps, as a question you asked, came, that will the band gaps fit to what we can realize experimentally and so on. The experimental realization itself, I mean, after having set up anyway the big experiment, to put the mirrors on piezos, that was not so tricky. And there, of course, one has, well, and I mean, there one has to synchronize, of course, because you want to have them 90-degree out of phase. But this is all in the kilohertz range, so that's not difficult to do. And that's where also Floquet engineering comes in by this shaking. And if you then calculate your effective Hamiltonian to second order, then you will get these additional terms, these next nearest neighbor couplings with a time phase, with a phase, and this phase will directly depend on the relative time phase of your piezos. So it's a bit like, I mean, in light polarization, you can also, I mean, it's also like, well, if you have two directions, and if they are out of phase, you get circular polarized. If they are in phase, you get linear polarized. So in a way, it is obvious. I mean, the experimental tricky thing is more that you still keep your whole lattice and all the interferometric stability of this X and Y beam, which you need to have phase stabilized, that still holds. That is the experimental trickiness, that your logs for this, that they accept this vibration. And then a nice aspect of the system is that you have a driven system in both cases. You can compare a driven with another driven system, not a driven with an undriven, because that due to heating, Floquet heating, we had heard that. Here you can compare either you drive with the same phase, and then you have just a band insulator or a churn number 0, or you drive with out of phase or the other out of phase. Well, yeah, one for the other or other way around, and those two situations you can compare, and then. Again, what you do, as in the graphene, you accelerate your cloud through the band structure, and then you measure the displacement. But now the trick is to avoid any kind of trivial displacement. You compare moving up and moving down, and then you take the difference between the two. So you detect the difference in the center of mass position for the two configurations. And that you can then do for the trivial situation. So you have a slightly a delta AB, you break your inversion symmetry, and then you see basically there is not a big drift. There's some noise on the data, something happening, but not much. And in the case that you open the gap by modulating, there you see that depending, you get either a drift to the right or a drift to the left, and you get the maxima exactly at that position where you expect. And then you can measure a phase diagram. So this is same coordinates as in the Haldane. So you have the phase here, and here you have the gap. But if you then you take all these measurements, and then you're a bit disappointed. Because if you then compare with theory, I think that would be this Haldane regions, they would be here somewhere and here. And then you think about it, okay, well, it's nice that you get all the symmetries correct. But the actual displacement of your cloud, if you have not very far open gaps, and what is happening if parts of the atoms actually move into the higher band, they cross the gap, and then see the other Berry curvature, that can lead to I mean, also in simple calculations, we could see that it actually leads to an extension of that region. So my question is now to you, how can you then, what is an alternative method to measure this phase diagram? Because it would be nice somehow. One has set up everything, one thinks, well, it's true, it works. So what could one do? What other method could one use to measure?
I guess circular dichroism, it's something that also related to the churn number. So I'm not sure in this system it's possible to do, circular dichroism measurements.
And I think there is a nice measurement done by the Hamburg group on circular dichroism. Yes, and yeah, where they look at excitations, well, in one direction, additional oscillation would that mean here, and then measuring, I think, the frequency spectrum in one direction versus the other direction.
I see.
But there is also a method which actually we kind of had looked at already. Maybe, yeah, you think about what we've learned so far. What could
so it's just about the band population, like.
Yeah.
Maybe the question first, so are you filling the lowest band with let's say fermions or?
Yes, I'm in the lowest band, yes. Yeah.
But are you filling the lowest band?
well, it's a trap. So in the center, kind of, it's filled, and further outside, not. So you can think also of more like a wave packet, but which doesn't go to the higher band. Yeah. So it's not fully filled. Yeah. Or I mean, there are regions where it's filled, but regions which are not filled. Yeah. So what? Yeah.
So you mean
Yeah.
the arrow now comes from the population to the higher bands?
Yes.
So maybe you can do the same thing for the system with or without the direct point, so that you can make the difference to get rid of the extra band population to the higher band.
Yes. So one could use this feature that you have at these regions where your phases end, or where you have you go from one phase to another, there are Dirac point closes, and now one can wonder whether one can measure that, and that is kind of promising, because we saw in the data for the graphene we could resolve both Dirac points, and now one should have some data where one Dirac point closes, or where I have crossing on one Dirac point, and at least much less crossing on the other Dirac point. And that's exactly this type of measurement we have done. And then you get pictures like this, that is, say, here is transfer from one Dirac point in the higher band, and here from the other one. And then you look at, you can count these atom numbers, and now you can change your parameter and look where is the maximum transfer as a function, say, of you take a given phase, but you vary your inversion symmetry from shot to shot. And then you get a phase diagram that looks like, that looks like this. And there you see, this here is a point, well, the orange versus green is upper or lower Dirac point. And here they are at the same point, they have the maximum, and that corresponds, here should be an arrow, so that goes to this point. And here, for example, you have here, as a function of delta AB, the inversion symmetry, you have the maxima at different points, and that corresponds to these points. And that now agrees fairly well with the theoretical expectation. So the bold line kind of is in the center. These dashed lines are, well, the limited knowledge that we have on our absolute knowledge on our parameters in our system. So maybe one more question to you.
Sorry, can I ask a question before you ask a question?
Sure. Yeah.
So for both this picture and the previous picture, which was a drift essentially measured. So is there like a calculation that shows that they supposed to be somehow proportional to Chern number?
I mean, in which say, I mean, there is, I mean, one can do the calculation where you have in this case here, you can calculate where you have in your parameter space your back gap closing, and then in this sense you measure the maximum transfer. So you measure where is the point where the gaps must have come closest. In that sense, that measurement is where is the point where the upper band, the upper Dirac point has come closest and is opening up before it opens up again, and the same for the lower.
So in other words, you're not really measuring directly churn number or invariant. You're really measuring the band closing points.
Sure.
So the point is that if your system has a multiple band, then that band closing could come at some other energies, right? Not necessarily low energy bands. So if you have like a 5 bands in the system, then there might be a band closing between a band number 4 and 5 instead of 3 and 4.
But in this case, here we know that we are in the lowest band. And then we, of course, we change our parameter, this tunnel matrix element, that is our horizontal parameter. And then we see the change in this tunnel matrix element.
Interesting, I see.
Which is, not too bad, I think.
That's cool, yeah.
And concerning the transfer measurements, so the drift measurements, that needs more, I mean, to do their full simulations, that is some effort. But well, simple simulations that we did to see whether the tendency that what we see is the right one, and that was the right one.
Yeah, thank you.
Further questions? Maybe a question to you again. So these topological systems are, of course, often also associated with edge states. And now one could wonder, how can I construct in a similar system, and well, by modifications to that system, how can I construct an edge state? What could one do? How, So feel free to well, I'll have something to drink here, and then feel free to think 2 or 3 minutes.
Sorry, you mean experimentally how you can?
Experimentally, yes. How could, well, you know, I mean, first, what do I need in principle? And then we can still try to figure out how to implement it experimentally. I mean, it depends on, one can attack the problem from different sides.
Well, I think, well, I mean, theoretically speaking, you need to have a open boundary condition. Somehow you have to impose boundary condition, open boundary condition in the system to see the edges. Otherwise, but I don't know how experimental is possible.
Further, thoughts? How could I get?
Could you use a magnetic field to create that boundary?
Let's think. So if I have a magnetic field or field gradient, but there I would, okay, my skepticism, but I'm not sure because I have not thought it through, I might be a too early skepticism, is that I would have the same gradient everywhere. So I would everywhere have the same system.
So it would become like the force rather than sort of an on-site field that would change.
Yes. But with, space-dependent gradients is in the chat. That's a good idea. So what would a space-dependent gradient do? What would that? Any suggestions?
Do you want to speak up about the space-dependent gradient?
So change, exactly. So a change in delta at some location across, yes, I can't unmute. Okay, yeah, sure. Absolutely. So it would change in some location this delta, okay? And that means I can see it directly here, that then by changing, if I'm here in the topological insulator, and I go to a region where my delta change from here to there, then I go out of the topological insulator. Then, yeah, and then I should have an edge. I think every theorist would agree that it should at least be something like an edge. We have not really an infinite system or so, but it should be an edge type. And there was, I mean, a giant, okay, yeah. Okay, yeah, so I think that's a very good answer. So we looked at, well, maybe one could still have another implementation suggestion. I think conceptually it's exactly the right thing. And
how about defects? I mean, defects essentially are look like an edge. So if you add like I don't know if it's possible to add dislocation. In metamaterial, people do that, but if you be able to add a dislocation in the system.
Yes, yeah, that's a bit, with these dislocations, we have a bit of problem in our optical lattices. It would be nice to be able to do more. Well, one could do something, of course, with microscopes from above. Yes, I think, yes. Okay.
Sorry.
Yeah, sure.
Is it possible to directly apply, like, let's say, the box potentials? You directly have the edges. You don't have the box potentials. Oh, it's very difficult.
So let's assume we have a box. Does that give a topological edge or not? So I need to ask you.
Yeah, I mean, firstly, you have this topological insulators realized, and then you impose some box potential so that you isolate the systems. You will have a sharp edges.
Yes.
Or maybe you have some interface between topological trivial and non-trivial states.
Yes, I mean, the interface there, I have a clearer picture. With the box, I have less clear picture, and whether I have to count whether I have an even or odd number of lattices or something like that. I simply have not. Yeah, I don't have a clear picture. You have to ask Nigel tomorrow.
Yeah, thanks.
Yeah, and the one thing we thought of about kind of which is experimentally relatively realistic, not super simple, but relatively realistic, that is a situation where you have laser beams which have a different wavelengths, so that you have the condition of inversion symmetry, say, only in the center of the trap. And then when you go outside, you no longer have that. And to make that round, we came to the conclusion we have this additional beam to focus more if we want really to have a round edge. And I think that is more or less very similar to the suggestion with the magnetic field that came. And then one can, well, here is a calculation of what it looks like, and then one can also make calculations that where you put a wave packet in and then oscillate or can have it oscillating on this edge. At least that's theory. That's not done in the experiment. It's a not so easy experiment, I think. And
before we continue, I just wanted to note that we should maybe start wrapping up in the next few minutes since it's getting to be that time.
Yes, and that's why I want to thank. I mean, all the work which we do here is, of course, with all the students over there. I mean, there are more people than there are right now in the group, but there are a lot of people, of course, who have contributed, and this optical lattice team that's here on the upper left corner. And the postdoc at the moment on this team, that's Konrad Fieban. And I would like to thank them all very much, because it's always stimulating discussions and ideas they bring in and bounce. Okay, so.
Great, so thanks, Tilman. And let's have all the questions we want to ask here. This leaves, we started a bit late, so we still have some time for questions.
Sure.
Jaren?
Hi. So I was curious whether there is a direct way of measuring the Chern number. So and then I was thinking maybe if you if you can measure the edge states, then you can, I guess, discern the Chern number from the edge states.
Yes.
That comes to the question of like measuring the edge states, I guess. But also like another question, whether there are other ways of measuring the Chern number in AMO systems.
Yes, there is. I mean, Monika Eidelsberger did a measurement of the Chern number in the Harper-Hofstetter. And it's also out of a drift measurement, but it was a more quantified drift measurement. So there was a more direct comparison what you expect and what you, taken into account as many as possible effects. And they got a very precise value for the Chern number.
I see. So it's really like quantized. I'm sorry.
So I was just going to say, I think what you were about to say, Jaren, that if you look at the edge states, then actually the conductance, the conductance is quantized according to the Chern number, right? So it tells you the number of one-dimensional channels you have, and so in principle that gives you a way of measuring this. And Tilman is the expert of measuring conductance and one-dimensional channels, but those are quite different experiments. So I don't know how feasible you can do that in these experiments.
Well, I think it would, the question is how can one maybe make in the channel in between the two reservoirs, whether one can do there a quantum Hall type of model. And if one there has a good idea, we have a proposal, but the proposal is has some experimental challenges.
but even in the 2D system, is there any way to actually measure the conductance of the edge states?
I think the conductance, I think one could, I mean, you need to feed into the edge somehow. I mean, I think it would be a fairly similar measure, and then, well, you might measure the current and then a voltage by a shift in total. I guess something like that could work, yes. So, yeah, it would be, it's still, of course, we keep thinking about how could we do that and how could one, and interactions are, of course, one of the big challenges.
Thank you.
And there, I think it's also important to mention that most of these measurements were not done in a Hubbard regime, but in tubes, so that you have 2D lattices where, in effect, the third dimension are tubes. And we can do, the system is robust to some extent also in a Hubbard system that we have looked at. but we could not do the Bloch oscillations in the Hubbard system, and that had to do with the, I think somehow with the gaps. I can't remember exactly the reason. It's probably, yeah, I can't remember. There was a specific reason why it's more difficult in the lattice to apply. I think, it's simple. Yeah, it's very simple. No, the problem is if you want to have interactions, then you of course need to have both spin states, and both spin state. Well, the spin states have different magnetic moment, and then they have different experience different gradients, and then yeah.
Other questions? So I was wondering about, I think everything you've discussed here is in the tight binding regime, but these topological bands and things also exist even in a weak lattice, right? So where tight binding is a very bad approximation and you just have a very weak potential. I think Dallas originally did this, or somebody. Could we explore that, or is there a reason we've looked?
We are not so much in tight binding, actually. The picture is usually easier in tight binding, but it's not, it's not, deep tight binding or anything. Yeah, it's
what is your lattice depth here? Maybe I missed that.
What was the lattice steps? Oh, that's a long time ago, but I have.
But like a few recoils or something. It's not.
Yes, a few recoils. That's exactly. Yeah, I would have to look it up to give a true answer. So yeah, so I don't. Yeah, it probably takes a moment.
Sure. Yeah, no, that's fine.
But it's not. It's not. I think one can just think of tight binding, but not deep tight binding.
Well, I guess so. I'm not sure the case for the sort of the band structures you've been looking at in Haldane model, but if you were to just do this for the ordinary Hofstadter problem, when you look at the bands in the Hofstadter limit, the tight binding limit, and you look at this weak lattice limit, the shapes are completely different, right? So they're both these very kind of weird fractal things, but there's some real change as you go from one limit to the other. And so that's kind of why I was wondering, if you could see something qualitatively change as you move away from that tight binding limit.
Yes.
So any last questions here before we adjourn for lunch? All right, so it looks like that's a great place to stop, and we'll see Tilman again tomorrow morning. We will reconvene after lunch at 2 p.m. Mountain Time, I believe, for David Hughes, and then Chris Monroe will give his last lecture this evening. So thanks, everyone, and see you later. Thanks, Tilman.
For me, it's 5 o'clock tomorrow again on my. It's the earlier slot again.
It's the same as you did on Wednesday, yesterday.
Okay, exactly. Okay, very good. Okay.